Hello, this is the first video of the Algorithm 3 series on further algorithms and efficiency for OCR Discrete Further Mathematics. This video considers efficiency and complexity in terms of run times and algorithm orders. The efficiency of an algorithm is a measure of how long the algorithm will take to run, i.e. runtime, denoted by t to the n, and is usually proportional to the number of operations that have to be carried out and/or the size. The size of a problem depends on the data going into it. For example, when sorting a list of numbers into order of magnitude, the size of a problem would be the quantity of numbers in the list. The order of an algorithm is a measure of the efficiency of the algorithm based on the size of a problem. Note that there is a distinction between the runtime, Tn, of an algorithm and its order. Complexity is a measure of the efficiency of an algorithm and may indicate whether runtime will be very long and/or require a large amount of storage space. Some algorithms will be more efficient than others, and that they will solve a problem using fewer operations. It's useful to compare algorithms, and we might do this by comparing the runtime of the algorithms for a given problem, or comparing the order of the algorithms. We need to note that more efficient programs will use less storage space when using computers, and that comparing the order is particularly useful as it allows us to make very general comparisons, especially for larger or real-world problems. This hierarchy of orders is defined as shown here and given in the formula booklet on page 13. Note that this sign means subset of, so the higher orders are shown on the right hand side. So for example, if you have a polynomial expression for the runtime, that will take less time than a factorial expression. The lower the order, the faster to run the algorithm, especially when the size of a problem is larger. In this example, we have two algorithms that are available to solve a network problem with n nodes, in other words, size n. Algorithm A has time complexity function t1 of n equal to n cubed plus 3 log to the base 2 of n. While algorithm B has time complexity function t2n equal to 20n squared plus 5n plus n log to the base 2 of n. We need to determine the order of each and hence which algorithm will be faster. The term higher in the hierarchy given dominates, so we would say that A was of order n cubed, because we can see that the log comes below the n cubed in the order, and that B is of order n squared, again because the n log n comes below n squared. Because n squared comes lower in the order than n cubed, B in general will therefore be faster. And as n increases, B should be relatively more efficient. However, it may not be the case for a small n. So here, if we compare the performance for two algorithms when n is relatively small, i.e. 10, and then as it increases to 100, we can see how this works. When n equals 10, t1 of 10 will equal 1, 0, 1, 0, but t2 of 10 will equal 2, 0, 8, 3. So therefore, for small n, A happens to be faster even though it is of higher order. However, once we get to n is 100, T1 of 100 is 1, 0, 0, 0, 0, 2, 0, compared to T2 of 100, which is still increased, but you can see that here the relative efficiency of B, being only order n squares, has kicked in, and so B, it takes considerably less time as n increases to 100. Some examples of order for algorithms you have already met are here for polynomial order. Order of n squared is bubble sort, shuttle sort, and Dijkstra's algorithm, and order of n cubed, Prim's algorithm, and Kruskal's algorithm. Note that you should ensure that you are familiar with these orders. It is also useful to be aware, but not necessarily to know these, other orders. So, order of log to the n for the binary search algorithm, order of a to the n, for example for breaking an n-digit password of a possible symbols, and order of n factorial for solving the travelling salesperson problem by trying every possible Hamiltonian cycle. The latter will link to a later video on TSP, and where we will reconfirm why this method of checking every possible Hamiltonian cycle is not used in practice. In the next video, we will look at the quicksort sorting algorithm.